So today we're going to talk about some theorems about differentiable functions, and I'm going to give you a take-home quiz that will be due Friday. And Friday we're also going to have an in-class quiz on related rates. It's just the one problem. You already have it. It's the first page of your packet. So you can look at it ahead of time. The answer is on the back of that page, so you can make sure you'll know if you got it right. But to get full credit on it, you obviously have to show all the work and how to get there. And it will be a group quiz. Okay, so you can look at it, you can discuss it tomorrow in class, finalize everything. And then Monday, your data project is due, the linear regression project. Okay, so in this class, we're going to discuss 3 theorems about differentiable functions. We've got the mean value theorem, which is going to be new. The increasing function theorem, which is old. It's a theorem we've actually been using like almost the whole semester. We're just going to finally write it down and say it formally. And then the racetrack principle, which is also new. So some of today is going to be a bit more theoretical than usual, less calculation and more sort of conceptual. So you'll be strengthening new math muscles. So the mean value theorem. It says that if A is differentiable on AB, and remember differentiable means it has to be continuous and smooth, no sharp corners, right? Okay, so differentiable means continuous and smooth. Then if the function is differentiable on some interval A to B, so those are x values, remember, some interval on the x-axis, then there's at least one number C between A and B, so that f prime of C is f of B minus f of A all over B minus A. So if we think about what these numbers, what those quantities represent graphically, it's a much easier theorem to remember. So f prime of C, that represents the slope of a tangent line at x equals C, right? What does f of B minus f of A over B minus A represent? It's the slope of what? It's definitely a slope because that's a change in y over change in x. Go ahead. The secant line, yeah, slope of a secant line that connects the points at A and B. Okay, so we've got a tangent line. Slope of a tangent line equals the slope of a secant line. What do lines that have the same slope look like? They're parallel, yeah, they're parallel. So this says that if you draw the secant line from A to B, so I'm going to draw this in here, connect A and B with a secant line, the points on the function at x equals A and x equals B. So there is some line parallel to that secant line that's a tangent to the curve, right? So I can find somewhere between A and B a value of C so that I could draw a parallel tangent line. So it looks like in this case it would be approximately here-ish. If I draw the tangent line there, that was bad. So if I draw a tangent line here, looks pretty parallel. So what my theorem says is that as long as my function is smooth and continuous, if you draw a secant line to connect the endpoints A to B, there will always be some value C in between A and B so that the slope of the tangent line at C is the same as the slope of the secant line. In English, there's some tangent line that's parallel to the secant line. So let's have a little look at a better, since I'm not so good at drawing these things. Here's a little animation. Okay, so I've got a random function, f of x. And if I show a secant line connecting the points at A, comma f of A to B, comma f of B, just draw that secant line in. So its slope is about 0.8. You can see that right down here. And then if I drag this point x, there's got to be some place between A and B where the slope of this tangent line will be equal to the slope of this secant line. Okay, So I'm looking for a place where they're parallel, and then also this computer program is calculating the actual slope over here. So I'm looking for an actual slope of 0.8. So when I drag x, visually I'm looking for something parallel. So that looks pretty close to parallel, and its slope is pretty close to 0.8. So the x value there is 1.23. So the mean value theorem guarantees there's at least one c. Sometimes there's more than one, right? Sometimes there's more than one, but if the function's smooth and continuous, there's always at least one. But I could keep going and I can find another one over here. You won't always be able to find two, but that's pretty close to parallel. That tangent line is pretty close to parallel to that secant line, and you can see that its slope is 0.81. So my other c value is 2.78. So I found two values of c between a and b, where the secant line is parallel to the tangent line. All right, so that's the mean value theorem. All right, so this is a little intro to the racetrack principle, and we're going to talk about it in terms of an actual race. So let's say we have two zombies, Goeth and Hertz. They start a race in the exact same location at the exact same time. If during the race, Goeth was consistently shambling slower than Hertz, what can you conclude? Who wins the race? Hertz wins the race, yeah. So Hertz, and he not only wins, but he was ahead the whole time, right? They started in the exact same place. Hertz is moving faster than Goeth at every moment. So they were either at the exact same place when they started, and then after that, Hertz was always ahead. Hertz was ahead and he wins. Okay, so Hertz always ahead of Goeth and wins. Okay. All right, here's a slightly different scenario. We've got two zombies again, Goeth and Hertz. They complete a race in a photo finish. They finish in at the exact same time. Okay. And we know that during the race, Goeth was consistently shambling slower than Hertz. Okay, so Goeth was slower, but they finished in a tie. So what can you conclude there? Nope, he was always slower than Hertz.
Like a circular racetrack, he's on the inside though.
Something like that. He had a head start, yeah. The only way you can be running slower the whole time and finish at the same time as someone running faster than you is if you started ahead, right? So Goeth had a head start, right? And then that means that Hertz was behind. So Hertz is my right hand here. So Goeth had a head start, Hertz was behind, and then Hertz catches up, right? He's getting closer and closer and closer, and then they finish at the exact same moment. So Goeth was ahead the whole time. Goeth had a head start. Ahead the whole time. And at the very last moment, Hertz caught up. It could only have been at the very last moment that he caught up, because if he caught up before the finish line, he would have won, because he's always running faster. Okay, so this is the racetrack principle. So I'm using h and g as my functions for Hertz and Goeth's location on the track. And then h prime and g prime are going to represent their speeds, their running speeds, right? Because the derivative of position is velocity, right? Everybody okay with that? All right, so if this is an analogy for the racetrack principle, h and g are the position on the racetrack. H prime and g prime are going to be the speeds of Hertz and Goeth, how fast they're running. Okay, so the racetrack principle says that g and h are two functions, differentiable on a, b. G prime is always less than or equal to h prime, so Goeth is always slower than Hertz. Okay, so in both of those scenarios, Goeth was the slower zombie. Okay, so Goeth is running slower than Hertz all the time. Now, if they start in the exact same place, if Goeth and Hertz start at the same place at the same time, and Goeth is always running slower, then Hertz is always ahead and will always win, right? So the way I say that Hertz is always ahead is I say greater than or equal to, right? H of x is always bigger than g of x. A and B is the starting point and the end point of the race. Yeah. Those are x values. Think of them as the starting line and the finish line of the racetrack. Okay, and then this second one is analogous to the second scenario where the two zombies tie. So G of B equals H of B, meaning they finish at the same time, same place. Okay. And in that case, Goeth had a head start and stayed ahead the whole time until Hertz caught up at the very last minute. So Goeth was consistently ahead here. And I do put an or equal to because Hertz caught up at the very last moment. All right, so before I have you jump into the activities, who watched the video that was part of the, can somebody just summarize quickly for people who didn't watch the whole thing, what happened? Anybody? Yeah. So they both did a Rubik's Cube and then both ran a mile and it was a race, right? Yep. All right, so what was the result? Right. Uh-huh. Yeah, so like let's just say it was a virtual tie. Like I think the kid won by a little bit, but oh, Ian won?
Yeah.
Oh, sorry. Okay. Let's just
at the end had to put on a shirt that said IRW.
Oh, yeah. All right, so let's just call it a tie though. So this is how this applies to the racetrack principle, right? Is that if we're just considering the running part, right? After the Rubik's Cube part, the running race, Ian had a head start because he finished his Rubik's Cube faster, right? So Ian had a head start and it was basically a tie. It was basically a tie. Ian was running slower than his student, right? But Ian was ahead the whole time, right? So that's how the racetrack principle applies to that. Even though it wasn't quite a tie, it was pretty close. Okay, so your group activities are going to be pretty theoretical. Don't try to guess what I'm leading you to, right? Just answer each question one at a time, and then hopefully you'll see how it all fits together. Yeah.